Okay, I'll show you this short segment. Again, it was on CBS Evening News last night. It's a disorder called AFM. I believe it's acute. And again, the F, I'm not sure, but the M is myelitis. From the brief amount of time that we've spent with this content, what do we know about myelin? We've talked about two different types of cells in the nervous system that produce that. Can you name the two cells? One starts with an S, the other one starts with an O. Okay, no, myelin. I believe that we've started some of our presentations with that. So let me back up just a little bit. Okay. And we'll come back to that video here shortly. This information is important enough that we want to make sure. That's one. Okay. Yeah, the other one is oligodendrocytes. Okay, so here we're talking about this. Here we see the one Schwann cells, and again, that's in the peripheral nervous system. And then, if we back up one, here we see your oligodendrocytes, found in between that provide insulating layers of myelin around areas of the brain and spinal cord. Okay, now the reason that that's important is when you had seen the development of, was it Robert's brain? I think that was last week. We observed that on the overhead. When the brain is developing, it prunes itself. And what that means is you may have some connections, Gesundheit, that they may become detached in the infant brain as it develops, and then a new connection may be made. But the most efficient connection, what happens to the size of that axon? It's doing what? Getting bigger. So why does it do that? Well, it sends information more efficiently. The best signal that gets sent has a really thick coating of myelin. So then this disorder then of AFM, the M being myelitis, what do you think that pertains to then? Yes. What does that pertain to? Let's say you have bronchitis. What's that referring to? What about the lungs, though? What does it mean to have bronchitis? Well, that's going to be a result, but that means there's inflammation of fluid buildup inside the lungs. So then this myelitis is referring to, for some reason, and we don't know why, there must be something going wrong with the myelin coatings inside of these children as they're developing. And for some reason in Minnesota, it's becoming more and more of an issue. So I think I found that segment online. So I just wanted to give you somewhat of a brief introduction that some of the things that you do learn in this class, you may see on the national news. Well, that you understand what's maybe taking place. What caused that to go? Yeah, I don't know. That's just it. We're trying to, I suppose science is trying to figure this out.
showing up after he started recovering from the common cold.
I said, "Hey, buddy, can you lift your right arm?" And he goes, "I can't."
Elaine and Michael Young said soon after their now 4-year-old son Orville developed a fever in July, he started losing mobility in his right arm.
Can you feel it, buddy?
The Young say doctors ran several tests, but only got closer to a diagnosis after a second MRI.
And the results come back that he had an abnormality through his entire spinal cord.
Orville was diagnosed with acute flaccid myelitis, or AFM, and spent 6 days in the hospital. At his worst, the Young say Orville was unable to move the upper part of his right arm and had difficulty moving his legs and sitting up.
I just felt so sad for him that this thing that we didn't know about and we couldn't protect him from had happened and had taken a lot away from him.
Since mid-September, 6 children under the age of 10 were hospitalized and diagnosed with AFM in Minnesota. One possible way it can develop is from a viral infection.
It's very, very rare, and it's about 1 in a million.
Chris Earsman with the Minnesota Department of Health says AFM affects the spinal cord. Symptoms can include limb weakness, facial drooping, and trouble swallowing or speaking.
If you have a child that is having these kind of symptoms, they should be evaluated immediately.
The Young say Orville has regained most of his muscle function, except in his upper right arm. They don't know if he'll be able to move it again.
How confusing is this to him?
You know, he's a trooper.
He's remarkably, able to wrap his head around this as it's going on. You know, he's kind of like one day at a time, whereas we're worried about the whole rest of his life.
Orville is in therapy and could need surgery later, but doctors don't know a lot about AFM right now, so there are no specific treatment options available. Health workers say one way to prevent this disease is to stay healthy. They recommend washing your hands and being up to date on vaccinations. Vlad?
All right, Jamie Yuccas, thank you very much, Jamie.
Hi, I'm Alexis Bennett, and I'm an
Sorry, what was that? Yeah, and what they're stating is probably stating obvious is to try to stay healthy. Well, with that, we associate polio is probably something that you've only heard of, and the reason I say that is we had believed, and I still think it's true, that the World Health Organization had eradicated polio. And what do we mean by when something becomes eradicated? Yeah, it's wiped out. It no longer exists. So with that, I want to say maybe in the 1950s to maybe the late 1960s is when this was probably finally dealt with and, like I said, eradicated. There's a certain world leader that had polio in World War II. Got us out of, well, possibly led us out of the Depression. Who would that be? Just take a guess. World War II time. Same name that took presidency over the turn of the century. There's a high school named after them in Sioux Falls, Roosevelt. Okay, so with that, okay, remember, what is it that's driving these action potentials? It's the movement of what ions? What's driving these action potentials? This is the process, but what two ions are we talking about? No. Got the right idea. But what's driving these actions? We said it's for instance, in a 3-to-2 ratio. And it's a couple ion. That's one. What's its next door neighbor on the periodic table in the same column? Okay, potassium's number 19, but what's number 11? Right above it. What's Na? How about sodium? Okay, so it's sodium and potassium that does this. Okay, so what we see happening here, the speed of a nerve impulse, we were just talking about that, is proportional to the diameter of that axon. So for some reason, if there's inflammation occurring inside this myelin, that signal is not going through, okay? Because this mother had said, okay, can you, they kept saying buddy all the time. I can't remember what his real name was. I said, buddy this, buddy that. I said, buddy, can you lift your right arm? And he says, no, okay? So what that means then is possibly for some reason, this impulse connection is not getting sent to the muscles to do that. And as far as lifting your arm, it's not one of these muscles, it's your shoulder one up here. And it would be your deltoid. For some reason, that signal may not be getting through. That's a possible explanation. Again, I'm not a doctor by any means, but to me, that's what would make sense. This inflammation is not allowing that signal to get through. Okay, so we wanted to talk about the synapse then, okay? And what happens is some people, if they become paralyzed by a certain type of venom, okay? Could be maybe from a snake, a scorpion, any type of neurotoxin could possibly cause this to happen. Now I remember what it is. I believe it's the this guy's close cousin. This is a green species. The black one can cause this. Don't say black snake, but we're not snake people. I get that, but the student who gave me these last year certainly was into animals. You probably know who it is. He played football here. Keith, he gave me those gave me those folders, okay? So that is the green mamba, and it's the black mamba that has this neurotoxin that interferes with this signal here, okay? And we'll show you what that means here. You're gonna have to, sorry, you're gonna have to put up with some of my artwork, which really isn't the best, but we'll try to make sense of what's happening here, okay? So I want to do this one, and then we'll stop at the end of this. But I'm going to draw something up on the board to try to make sense of this. Okay, does everyone have this information that wants it? Okay, so let's try to make sense of what it is that we've been talking about here. Okay, so if we just have this very basic nerve cell, okay, or neuron, okay, so we got this structure here that's really, really thick. What's causing this thickness to occur, become thicker and thicker and thicker, or more thick? Starts with an M. It's myelin is the material, okay? So remember, what we see happening here is outside of this cell body, we've got lots of this, okay? We've got lots of sodium. And if my interpretation's correct, which I'm hoping, I shouldn't say hoping, I believe that it is, we got lots of sodium on the outside, and then we've got this on the inside. And we got a little bit out here, okay? And I'll maybe put one more, okay? And then we've got a little bit of this sodium on the inside here as well. Okay? So remember, we're talking about this action potential. We say it's kind of like a wave. If you've ever been to, give me some athletic events you may have gone to. Maybe it's none. I don't know. Okay? Maybe up at Brookings, up at State. Okay? They probably don't do the wave there. Oh, they do. So have you taken part in that? So do you get up and you do that too? Oh, so probably would not be very conducive. But the idea is not everyone's doing this at the same time, are they? No, because as you see it coming, then you stand up. If you can, if you want to take part, then you do this, and then it goes moving around in a circle, and then you see it coming, or maybe it's coming back, and you stand up and do this. Okay, so what this is doing is this is the wave with action potentials going in this direction. Why do we know that? What is this structure called? Because here's another neuron. We said this comes to a point about like that. Because this is sending the signal that way, making this what type of structure of the neuron? Starts with an A. It's the axon. And then that comes to a terminal end right here, because this is receiving the information. What is this called? This is the dendrite. This is, we'll just say, the axon. Okay? So what happens is this diffuses, pretty simply, some of this sodium, okay, comes in through some of these channels here. So even though those three may have diffused through there, that does it very easily because it's going downhill. Look at all this sodium you have on the outside of this axon. Look at how little sodium that you see in here. It's pretty easy to, let's say, pedal your bike downhill. Everyone can do that. I mean, you'd rather be at a slight incline like this. You don't have to pedal so hard. So this sodium diffuses through very easily. So now we've got some of this sodium on the inside. Okay. So those three are gone, but what we still see happening though, this one, we'll say this one, is there still more is there more sodium on the inside or on the outside? There's still more on the outside. So what has to happen is this sodium has to be actively pumped against its gradient. So the potassium will do the same thing. It diffuses through here very easily. Okay? But notice we have, and then this potassium then diffuses through. Is anybody lost right now? We're saying, what is he talking about? He's pointing arrows here. He's saying this diffuses through, and we got the sodium and potassium. Okay, so what that means then, this potassium and this potassium are now gone because they diffuse through there. Okay? Because it very easily, you have all this potassium on the inside and very little on the outside. But now, this has to be pumped against its gradient again. Okay? So this sodium has to be pumped out, 3. 2 of those potassiums have to be pumped back in. So what that does is that creates a voltage difference, and that's why you see that action potential going, because there's a charge causing that action potential to keep on moving because of this influx of sodium and potassium into and out of the axon. Now, this is different when it comes to that of the synapse. What did it say that it doesn't go to a dendrite, okay, rather than go to a motor end plate, okay? The distal ends of neurons have one or more extension called synaptical knobs. These knobs are absent in dendrites, okay? So what that means then, okay, is maybe you could look at it as, here we got this neuron, this is the very last one, and we've got this muscle tissue down here. This is a muscle cell. And we'll put all the striations in there. Oops, I did that wrong. It goes the other way. No, that's right. Okay. So then, this is why it's called a synaptical knob, is because once this signal gets down to this area, this is called a synaptical cleft. That's what we're talking about right here. Okay, sorry about all this synaptical vesicles, synaptical knobs, and this is the synaptical cleft right there. And what happens is, as this wave keeps going, it will stimulate this muscle cell because of what does that say? What's that called? How do you think you pronounce that? Acetylcholine. Well, what does acetylcholine do? Well, maybe it's not on, oh, well, okay. It's a biochemical message that stimulates muscle cells at the synaptical cleft. Maybe let's pull this down here. Maybe we can see it a little better, okay? Acetylcholine is a neurotransmitter, and what it does, it's a biochemical message that's responsible for the stimulation of muscles at the synaptic cleft. The distal ends of the neurons have one or more extension called synaptical knobs. Okay, so what that means is, as this signal, rather than going to another neuron, it's going to stimulate this muscle cell at the synaptical cleft. I'm giving up on trying to say that. I'm putting AL at the end. Synaptic cleft. So once this reaches this terminal end, it sends a neurotransmitter in the form of acetylcholine to stimulate that muscle cell. Okay? Because what do muscles do? Do they push or do they pull? So see those red dashed lines? Okay, so these are my fingers, are those red dashed lines. Do they push apart or do they pull together? They pull together. You're right the first time. Muscles don't push, they pull. Okay, and sometimes you might be thinking, well, if I'm doing push-ups or if I'm doing a bench press, we're pushing them up. Well, that's true, but your biceps is what shortens this angle. It's your biceps that extend that angle. Okay, so we will continue with this on Thursday, because tomorrow we'll be on our way to Irene, and then we'll continue with this synapse on Thursday.